Hello, I'd like to go over the ratio of pi, and if you haven't seen yet, please refer to my Math Paradox Finally Explained video, where I go through the difference of why ratios work to preserve the unity and integrity of the structure, whereas division processes don't, since they're reliant on the number system. And in our case, the number system is based on tens, and in our case, the number system can also be counted infinitely. And therefore, there's no limitation to how many segments any particular line can be broken into, since they could be broken into infinite number of points. For example, this line over here, according to the number system, I could break it into as many tiny dots as I want, and I could split those dots in half and in half and in half. So this line could be infinitely long or infinitely broken into pieces according to our number system that allows that to happen. And that's why we have calculus to kind of make those points so close together, per se, that they kind of redefine this line. Instead of having a more beaded appearance, if we make these tiny little dots small enough, then it becomes kind of like a continuous line, and that's kind of like what calculus is performing for us. But anyways, let's go and look at this circle here, where we're going to say that the distance around the circle is the circumference, and we'll call it c. And by the way, these are definitions once again. We didn't have to define these things as such, but this is what we're saying. The around will be called c, and across one time the fattest part of the circle is going to be called d, or for diameter. And then utilizing the math rules, this is the ratio, we'll call it's pi is the ratio of the circumference to the diameter. This is a definition. If we solve for circumference, then we can see that circumference equals this ratio times the diameter. Or if we solve for the diameter, we can see that the diameter equals the circumference divided by this ratio pi, which pi is just someone like that measured the distance around the circle, kind of took out the circle and made and took this, instead of making a circle, we could straighten it out into a line, and it would be that long per se if we straighten it out completely. And then we have the diameter, and it's that long. And if we put this into that, it's going to go in approximately, we'll go in 3 times completely, and then we're going to have the problem of the little bit left over. This is the same problem that we ran into in the paradox lecture that I just referred you to. So if you can look at that, you'll see why only ratios work, whereas if we try to deal with that last little bit that's left over, we run into the problem that now we have to deal with the number system that we're dealing with. So in other words, if I keep this whole, and this is c, if I say, okay, d diameter is this much of the circumference, and I keep it on the same line, that's fine. Then it equals that much of this. But once I try to break it up into numbers, now it's going to depend on us. So if we're going to say, okay, well, we'll make c, we'll define these units as 1, 2, and 3, and we'll define the length of 1 as d. Well, then d is going to go into that 1 complete time, 2 complete times, and 3 complete times. And now we run into our problem of what to do with that last little bit. Well, when we keep it as just a ratio, it's not a problem that it's this much out of the total, because now unity is kept. We're keeping the whole thing intact. But when we try and define it with a number system, we get into a problem, because this last bit can't be defined with these segments of 1. Whereas that part went that much, and that part went exactly that much, and that part went exactly that much. We have this extra little bit, which I could call delta x, and represent there. And when I try to put that in, it won't fit. So in order to make it fit, we have to do the same tricks as we did last time and try and make up some kind of number system that will describe this extra little bit. So it doesn't fit into the smaller one. And basically, so how are we going to describe it then? Well, the only thing we can do then is to describe it with the number system that we have. So how we're going to break up that little extra delta x is going to be dependent on what we do it. If I take that little delta x and I split it in half, and I have this other thing I'm trying to put into it, and I cut it the same amount of times, I won't get as much accurate of a number if if I took the delta x and I split it in this many times, utilizing this kind of thing. Then I could get a more accurate, because the thickness of this line is like this, so that's how much of an error I have now if I split it in half. Whereas now I only have this smaller amount as my potential error in the difference. And of course, we can take these little lines and chop them up infinitely in our mathematician language, so that this delta x, this difference here, that's getting smaller and smaller, approaches infinity. But it can't get to infinity because there's no amount of times I could cut up this line. According to math, I could infinitely cut up the line. So that's where the problem arises. And now we have the same issue as before, where we can only approximate a ratio with numbers, that we can't get rid of these infinite slices to recreate the line, because you could keep making it smaller and smaller. You can make it quantum mechanically small, and it just keeps going and going and going. And we could come up with more and more symbols for it. But the concept of the ratio will remain intact if we present it in this way. But once you deal with number systems, there's no limit to how many times we could chop up our number system. So the approximation will be based on the number system itself. So for example, if I had a number system that I created a new one, which only had two numbers, 1 and 2, and I called the halfway point here, and if I took our current number system, which is based on 10, and I converted to a number system based on 2, well, the issue is going to arise what's going to happen when I get halfway between. So in the first case, I'm going to define this in my new number system, this 3.1415. So anything less than 5, I'm going to call 1. So this would be 1.111. Well, now I have the 5. So do I go up to this, or do I go down to that? So that becomes a question mark, because we don't know. We didn't define it yet in our language yet. And then I'll have 2 and 2, because 9 is greater than 5. And actually, this should not be 2. This should be 1, because I got faked out. This is less than 5, so this should be 1. Unless, hold on, unless I skipped one. I'm sorry. Wait. 3, this is less than 5, less than 5, less than 5, less than 5. No, that's correct. Then I get the question mark. I'm up to here. And then 9 is greater. Oh, then I made the mistake. Here should be 1, because 2 is less than 5. I'm off by a number. I'm very sorry about that. But this should be a 2, because it's greater than 5. And now I have 5, which was going to be a question mark. And then 3 is going to be 1, and 5 is question mark, and 9 will be 2 on my new number system. Now, if I decided to make these question marks that were at 5, And I said, okay, now I'll make my new definition of my number system, and I'm going to say, well, 5 and under, I'm going to include 5 and under that'll get rounded to the 1. Then these become 1s. Or I could do the opposite and say, I'm going to do 5 and greater, I'm going to assign for 2. Then I'll get these question marks, and this should be a 2. And this is a 2, and this is a 2, to go up to 2. Of course, this number, so to say, is different than that number because it's less chopped up. So it's not giving as much information. All we're stuck with now are this distances, whereas before we were splitting it up into these smaller distances. So we still have information here, but it's not as chopped up and accurate as that, and certainly not as good as calculus could give us, where we have this approach 0 but not touch 0. So in the case of if this is 1 and this extra is x, I think I'm just kind of going over the same concept here, where we have this extra little bit, delta x, and we're saying anything that goes over this 1 mark gets converted to a 2. So this becomes our arbitrary point right at there. And that's where we ran into the same issue, what to do when it gets to 5. Do we keep it non-defined? Do we round it down to 1? Or do we round it up to 2? And basically that's what's happening with number systems. How fine you want to chop it up. I could have made this length, I could have made, okay, this length equals 1, 2, 3, or I could have chopped it up into 1, 2, 3, 4, or 10, or 11. But we have a length, and the length defined by numbers can go to infinity as the delta x approaches 0. These distances get smaller and smaller and smaller and smaller. The only thing that's going to happen is we're dealing with the language now of how we're chopping this up. The actual ratio of this to that is going to remain the same, because now we're dealing with the same concept in the other lecture, that the ratio gets preserved. But when we try and define things with finite numbers, and our number system is based on 10, so how can we possibly describe this line if we're chopping it up by tens or even by hundreds or thousands, because there's no way to define the line with a number system. The line is this length. And, depending if we made our ruler a 12-inch ruler, or we can make it a 24-inch ruler, or I don't know, we can make the ruler millimeters, and that would change it. Now we're dealing, instead of inches, we're dealing with millimeters. We get to define how we want to chop up the line. But the line itself is defined, and that's defined as the circumference. That's the definition. How we chop it up is up to us. That's our number system. We decided to make a number system out of 10. It was based on consensus. It used to be the Roman numeral systems with letters and symbols and such that, but we've changed it, and most people are using this 10-based system to chop things up. So the language is what's going on here. The ratio is always going to work, and we can define the ratio of this to this as pi, and we'll make that symbol. But to describe it in numbers, we run into the exact same problem, because we can't. There's no shortage to how we can chop up these numbers, and also how we define our number system is completely up to us. We're just so used to seeing this number system that we think that it's or at least I thought until a long time, it took me a long time to untrain myself, that this was an answer. But this is not an answer. This is an answer based upon the language that we created. This could have been an answer, because it's dealing with the same length concepts. We have to keep to the concept of concepts and start forgetting about numbers, because the numbers themselves don't have the intrinsic truth that the actual ratio is showing us. The numbers are just a way to describe something. And our number system is based on 10, but here it was based on 2, and we can see why the issue is happening. The same thing goes for the Pythagorean theory, and we have that formula a squared plus b squared plus c squared, where we could make this into a whole square, and we can say, I referred you to the proof, but this came out to, if we make a 1 and a 1 here as the opposite and the adjacent. So this is the Pythagorean theorem, and 1 squared plus 1 squared equals c squared if we assign that. So we do, okay, so 2 equals c squared, and c equals the square root of 2. I took the square root of both sides. So square root of 2 works if we keep it as square root of 2, representing the symbol of the ratio that represents this length as compared to that length and that length. This would be the whole length of the 1 and the 1, and we keep the ratio of this, and we'll call it square root of 2, but we're just assigning it the concept that that goes, if it's kept all the same, it remains within the whole that much times. But as in the other case, if we try and define this extra bit that's left over, well, it's somewhere in between this length of 1, this extra bit. So now we're stuck. Well, this 1 goes in the exact time, like here, and then we got this extra bit. And so what do we do with that extra bit is going to be dependent, again, on the number system. Because that doesn't go exactly into that, and that doesn't go into that exactly. We could define something that goes exact, but then we're left over with this extra stuff. And then again, we have to use the number system to deal with that. So when we keep it as a ratio, square root of 2 represents the ratio just like pi did, and it works. But if you try to chop up the square root of 2 into something, we're again stuck with the same situation, where how we chop it up and how we define our number system is going to be what we see. Because this delta x, I could chop it up and I could say 1, 2, 3, or I could chop it up and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Or the same thing, I could make that delta x, and I can make it a B, C, D, E, F, divided by this. But because this length that we defined as the 1 doesn't work with this anymore, the unity is broken. Now, in order to deal with the leftover, we have to rely, or we don't have to, but we have a number system now that we're going to deal with. And our language, which is just a language, is based on the number system of 10. So there you have it. I hope you've enjoyed this, and there'll be more lectures to come. Thank you.